Machine learning tasks generally fall into two categories. You can train a model to sort data into rigid categories, like flagging an email as spam, or forecast a fluid, shifting range of numbers. Linear regression is designed exclusively for the numbers on the right. It estimates continuous outcomes, like a temperature reading, a future stock price, or an upcoming exam score. To build this model, we need two foundational elements. First is the input, the independent variable, also known as the predictor, which we designate as X. Second is the target output, the dependent variable, or the response, designated as Y. This is the continuous value the model tries to predict, which changes in relation to the predictor. Before doing any math, an analyst must strictly define these two roles. You have to know exactly what input is doing the predicting and what continuous reality is being predicted. This chart shows how these variables look in the real world, messy and scattered. Here, we plot hours studied on the x-axis against the resulting exam scores on the y-axis. If a roughly linear pattern exists within this cloud of data, we can draw a straight line of best fit straight through the center of the cluster. That visual line immediately translates into a universal mathematical equation, y equals mx plus c. The equation takes a given x value, applies a specific rule, and outputs a continuous predicted y value. That is the core mechanism of linear regression. It takes observed historical scatter and turns it into a usable, predictive mathematical rule. How does the model place this line? The goal is to minimize the distance to every observed point. It measures the vertical gaps from the dots to the line, stopping only when the average gap length reaches its absolute minimum. This line does not claim the relationship between studying and scores is perfect. It is simply the best straight-line approximation of the messy real-world data. To understand the physical reality this approximation represents, we need to deconstruct the resulting y equals mx plus c equation. The best fit line is ultimately a mathematical compromise, optimized to be as close to reality as statistically possible. We start with a slope, designated as m. This defines the exact rate of change. Mathematically, the slope shows exactly how much the predicted response, y, changes when the predictor, x, increases by exactly 1 unit. In our student data, if m equals 5, every extra hour studied increases the predicted exam score by 5 points. The slope's direction reveals the trend. A positive slope means y increases as x increases. A negative slope means y decreases. The slope dictates the physical impact of the predictor, turning the geometric angle of the line into a specific measurable rate of real-world change. Next is the intercept, designated as c, which defines the model's starting point. The mathematical definition is straightforward. It is the predicted value of the response when the predictor is exactly 0. In our exam model, if c equals 40, the model predicts a baseline score of 40 for a student who studied for 0 hours. However, you must evaluate the context carefully. Sometimes an x equals 0 scenario is unrealistic in the real world. This can render the intercept contextually meaningless, even though it remains mathematically necessary to anchor the line. Ultimately, the intercept locks the rate of change to a specific baseline reality, establishing the solid floor for the entire predictive model. Once the equation is set, we can actively use the model. To forecast a continuous outcome that was not originally observed, a new predictor value is substituted into the equation to find y. This makes linear regression useful for projecting future trends based on new inputs. But there is a strict boundary. A prediction is only trustworthy if the new x value falls within the range of the historical data already observed. Predicting outcomes far outside this observed range is called extrapolation. It assumes the trend continues indefinitely, introducing a major analytical risk. A machine learning prediction is tightly bound by the limits of the historical data it was trained on. Look at these two graphs side by side. An analyst must judge how reliably the model fits the messy real-world data. We measure this fit with a statistical metric known as R². It represents the percentage of variations successfully explained by the model. A higher R² means the points lie close to the line, making predictions highly accurate. A lower R² suggests the line fails to explain much of the real-world scatter. But remember, a high R² only proves a strong mathematical correlation. It never proves that the predictor causes the response. R² acts as the confidence score of the model, dictating whether the mathematical rule should actually be trusted to make decisions. To summarize, we identify an independent predictor, x, to estimate a continuous numerical response, y. The true skill in analysis is interpreting the exact rate of change, the slope, and the baseline starting point, the intercept, within the data's physical context. Always verify the model's reliability using R² and respect the boundary limits on the data to avoid extrapolation. Linear regression provides a highly structured framework for translating chaotic data trends into actionable